Welcome to the bonus video. This video is meant to include various details that I had left out of the series on the proof of Markov's theorem. I'll be starting with the history of Markov's theorem and the people involved. Then I'll mention the actual names of concepts that popped up in the videos, which I had referred to by different names for simplicity. Finally, we'll see two proofs that I had left out of the videos. One about why degree d polynomials can't intersect more than d times. And finally, a proof that the maximum slope of the degree d Shev is d squared. And there's going to be some really interesting mathematics in here. Let's go. Markov's theorem is formally stated like shown. The maximum slope that a degree d polynomial has when x ranges from -1 to 1 is at most d squared times the maximum value it takes when x ranges from -1 to 1. This is equivalent to the statement that degree d contestants have max slope d squared since polynomials can be scaled. It was formulated and proven by Markov, who is more famous for his work in probability theory. The fundamental Markov's inequality is from him, and so is the very widely used and fundamental concept of a Markov chain. Andrei Markov had a brother, Vladimir Markov, who actually extended Markov's theorem, finding out the maximum value higher order derivatives can take. P superscript k here refers to the kth derivative of p. This has a much more involved proof, and I do not know it. And you might be wondering which polynomial achieves the highest second derivative or third derivative and so on. The answer to that is that they're all achieved by the Shev. Let's move on to the Shev. We've already seen it in three forms, and now it's time to see it in its true form. I named those polynomials Shevs because they're actually called Chebyshev polynomials. They were named after their discoverer, Bafnuti Chebyshev. If you think you've seen this name before but spelled differently, I wouldn't be surprised. There are various spellings with which people have written his name. Chebyshev was the doctoral advisor of Markov and is also an important mathematical figure. He has the Chebyshev inequality named after him, which is another extremely useful inequality in probability theory. In fact, here's a quote from George Mackey talking about the history of probability theory. Chebyshev was the first to think systematically in terms of random variables and their expectations and moments. He's also the person who changed Bertrand's postulate into a theorem, showing that there's always a prime between n and 2n when n is at least 2. And of course he's famous for coming up with the Shev, or as R.P. Boas Jr. puts it, the Chebyshev polynomials. His interest in these polynomials were actually in creating mechanisms that move in a straight line. You can see gorgeous depictions and videos of some mechanisms he came up with at this link. The proof that I presented in this series was taken from an article by R.P. Boas Jr. called Inequalities for the Derivatives of Polynomials. I'd like to give a shout out to the friend of mine who went over this article with me. Thank you, friend. The article starts with the story of a Dmitry Mendeleev, some bloke who created something called the recurring desk or periodic table or something like that. This bloke was analyzing the specific gravity of mixtures of liquids and had some interesting observations in the data, which looked mostly like a quadratic curve. Following his curiosity, he did some mathematical analysis which amounted to proving Markov's theorem for quadratic polynomials. He then told his friend Andrei Markov of this mathematical result, which led Andrei Markov to prove Markov's theorem. It's a nice paper, linked in the description. That is it for the history. Let's do a rapid look at some of the concepts we encountered. I described the nth Chebyshev polynomial as the plot of cos of n theta drawn on a cylinder and projected onto a plane. A more concise mathematical way of describing that is to just directly compute the function value on the plane. At a point x between -1 and 1, we want to know what theta that corresponds to. We know x would be cos theta, so theta would just be cos inverse of x. And so the nth Chebyshev polynomial is merely cos of n times cos inverse of x. Cos inverse is also referred to as arccos, and that's easier to type on Desmos. Another way of coming up with the Chebyshev polynomial is recursively, as shown. You can try proving this recurrence for yourself. We also saw Laurent polynomials, but we call them fake polynomials. Sorry, Laurent. They are polynomials wherein the powers of x can be positive or negative. Now let's move on to the two missing proofs. How many times can two polynomials intersect? We claimed that the answer was the maximum of their degrees, regardless of whether the coefficients and inputs were real or whether they were complex. We'll see a proof now. The proof will be in two parts. The main part will show that a single degree d polynomial can have at most d roots, that is, d inputs on which the polynomial evaluates to 0. The next part will be to use this to conclude that 2 degree d polynomials can intersect at most d times. This second part will be really easy. Let's start with the first part. Take any polynomial, like this one with degree 6. If it doesn't have any roots, we're done. This polynomial does have at least one root though, the input 2. Our first step is to divide this polynomial by the polynomial x minus 2. The result of this will be very insightful. So how do we divide it by x minus 2? It's quite similar to normal division. Let's start with 0 multiples of x minus 2, so the whole polynomial is the remainder. And as long as we can extract multiples of x minus 2 from the remainder, we will do so. Notice that the leading term of the polynomial is 2x to the power 6. We also know that 2x to the power 5 times x minus 2 has leading term 2x to the power 6. So by removing this multiple of x minus 2, we would get rid of 2x to the 6 from the remainder. Let's do that. Add 2x to the 5 to the quotient and remove 2x to the 6 minus 4x to the 5 from the remainder. We can still remove a multiple of x minus 2 from the remainder, since the leading term is 6x to the 5. So we add 6x to the 4 to the quotient and remove 6x to the 5 minus 12x to the 4 from the remainder. Note that all we're doing in this process is multiplying, adding to the quotient, and subtracting from the remainder. We can continue doing this as long as the remainder has a term with an x in it. So when we end this division a few steps later, we'll end with a quotient polynomial, and the remainder will just be a number. Let's write that down in a simple equation. P of x is x minus 2 times the quotient, which I'm calling q of x, plus the remainder, which I'll call r. This is just the format you're bound to end up with after polynomial division by x minus 2. Now for a series of observations. Each one ought to be simple, and they'll finish part 1 of the proof. First off, q of x is a degree 5 polynomial, with the coefficient of x to the 5 being non-zero. That's clear from the way the polynomial division proceeded. Secondly, r must be equal to 0. This is because we know p of 2 is 0, and p of 2 would be 2 minus 2 times q of 2 plus r, which is equal to r. So p of x is in fact x minus 2 times q of x. Now for p of a to be 0, either a minus 2 must be 0 or q of a must be 0. If none of them are 0, then p of a won't be 0. A minus 2 will be 0 only if a is 2, and q of a will be 0 only if a is a root of q. So the roots of p are the input 2 along with the roots of q of x. P of x can have at most one root more than q of x. Now we can repeat this argument. A degree 5 polynomial can have at most one root more than some degree 4 polynomial, which can have at most one root more than some degree 3 polynomial, and so on. If we continue this argument, we reach the conclusion that a degree 6 polynomial has at most 6 roots more than a degree 0 polynomial where the coefficient of x to the 0 is non-zero. But a degree 0 polynomial with the coefficient of x to the 0 being non-zero is just a non-zero number. It can never be equal to 0 and hence has no roots. Hence the degree 6 polynomial has at most 6 roots, and the degree d polynomial would have at most d roots. We're now done with part 1. Part 2 is really simple. Say p of x and q of x are two polynomials of degree d. We can build the polynomial p of x minus q of x. It would also be of degree at most d. Now the statement a is a root of px minus q of x is the same as saying p of a is equal to q of a, which is the same as saying p of x and q of x intersect at a. Since p of x minus q of x has at most d roots, p of x and q of x can intersect at most d times. Now we want to make the same statement when the coefficients are complex and the inputs are complex. But you can go through each step of the proof and verify that the same argument would have gone through as is for complex numbers. In part 3, I mentioned a few properties that addition and multiplication of complex numbers had, and I said those properties made it good enough for the proof to go through. But there are actually many number systems beyond real numbers and complex numbers that also have all those properties. Here's one from Wikipedia, a number system with only 4 numbers: 0, I, A, and B. This table shows you how to add two of these numbers, like A plus I is B. And this table shows you how to multiply them. So now that addition and multiplication are defined, we can actually verify, if we wanted to, that those properties hold. There are many other number systems that are more convoluted that also satisfy these properties. Clearly, these are not numbers meant for counting like we usually have, but these systems have proven to be extremely useful, with uses ranging from cryptography to efficient COVID testing, to encoding your data in such a way that even with a few corruptions you can tell what the data originally was, enabling both QR codes and communication with the Voyager satellite. What we are going to do now is blind mathematics. We already did a version of this in school. We started with mathematics teaching us how to add numbers and multiply them. Then we went blind. We used letters in the place of numbers. And we started adding and multiplying numbers without even knowing what numbers we were adding or multiplying. And it was powerful and awesome. But at least we knew when we said x that it was referring to some integer or real number or something like that. This time, we're going even more blind. We don't even know what number system x is from. It could be a from this number system over here. Are you sure that a plus b times a minus b is a square minus b square? You can check it using the multiplication and addition tables here, but our intuition can't be trusted anymore. 1 plus 1 could be 0. All that we know, the only way in which we're not entirely blind, is that the number system satisfies these properties. So just using these properties shown here, we need to prove that a degree d polynomial will have at most d roots. We are going to have so much fun. Okay, so we have that some number a is a root of a degree d polynomial, p of x. We have no idea what kind of number a is. All we know is that p of a is equal to 0. But wait a second, does that even make sense? Is 0 even a number in the number system? If we look at our properties, we see that there is a 0, which is a number that doesn't change any other number when added to it. But what if there are two numbers with that property? Then it would be weird for me to just say p of x is equal to 0 without specifying which 0. So let's do our first blind proof now, that there can be only one 0. Suppose a and b are two numbers, both of which satisfy the property that they are 0. Now let's add a and b. Since b is a 0, that means this addition shouldn't change a. But since a is a 0, this shouldn't change b. If the sum is a, then a isn't a 0. And if the sum is b, then b isn't a 0. So both of them cannot be zeros, and there is only one 0. So it makes sense to say that p of a is 0. The polynomial x minus a still makes sense because we know that minus a exists. Our polynomial division just involved multiplication, addition, and subtraction. So although I'll skip going through this step in detail, it still is true that p of x can be written as x minus a times q of x plus r, where q of x is a polynomial of degree d minus 1, and r is just a number. Now our first claim is that r is equal to 0. Our logic earlier was that we know p of a is 0, and we also know p of a is a minus a multiplied by q of a plus r. By definition, a minus a is 0. That's what minus a means. So p of a is 0 multiplied by q of a plus r. Is 0 multiplied by q of a equal to 0? That's generally what we think of 0 as doing. But in our properties, 0 is just a number that has a special addition property, not a multiplication property. So now we'll have to prove that any number a times 0 is actually 0. We start by writing 0 as 0 plus 0, which is fine because adding 0 doesn't change 0. Then we use distributivity to expand this as a times 0 plus a times 0. Now we take the additive inverse of a times 0, which is minus of a times 0, and we add it to both sides. The left-hand side becomes 0 because of the definition of additive inverse. The right-hand side becomes a times 0, although to reach that conclusion, we have to do some rearrangement and simplification using associativity and the 0 property. Great. So now we know p of a is equal to 0 plus r, which is r. So because p of a is 0, r must be 0. Next up, if x minus a times q of a is 0, Does this mean that at least one of x minus a and q of a has to be 0? Basically, we're asking whether you can multiply two non-zero numbers to get 0. We'll prove now that if a and b are non-zero, a times b is also non-zero. Let's start by assuming that it is 0. We then multiply on both sides the multiplicative inverses of a and b, which we write as 1 by a and 1 by b. These exist because a and b are non-zero. Since we're multiplying by 0 on the right-hand side, the right-hand side becomes 0. On the left-hand side, with some rearrangements, we can simplify it to 1. I encourage you to do this rearrangement and simplification yourself. Now we've come to the conclusion that 0 is equal to 1. Is this possible? Yes, it is. But only in the case where our number system has only one number. In this case, that number will satisfy the 0 property, and it will also satisfy the 1 property. Again, I encourage you to prove that if your number system has more than one number, 0 must be different from 1. Given what we've already proven, it's quite simple. So if your number system has more than one number, then two non-zero numbers cannot multiply to give 0. If your number system has only one number, then there is no non-zero number, so the statement is still true. So every root of p of x must be a root of x minus a or be a root of q of x. If x minus a has at most one root, then again p of x can have at most one root more than q of x. So let's prove that now. We know x minus a is 0 when x equals to a by definition of minus a. If it is also possible when x is equal to some other number b, that means that minus a has two additive inverses. We'll prove now that every number has only one additive inverse. Suppose b and c are both additive inverses of a. Then a plus b is 0, and so is a plus c. Adding b to both sides, we get b plus b is equal to b plus a plus c. Doing a little rearrangement like we did earlier, we can add the b plus a on both sides to get 0 plus b is equal to 0 plus c, or b is equal to c. So b and c can't be different, and a has only one additive inverse. And so x minus a has only one root. So again, we've reached the point where we can say that a degree d polynomial has at most d roots, more than a non-zero degree 0 polynomial. A non-zero degree 0 polynomial can never be equal to 0, and so it has 0 roots. And this finishes part 1 of the proof. Part 2 was to say that two degree d polynomials intersect at most d times. This proof didn't look at what number we were using. It just used the fact that if p of a minus q of a was 0, then p of a is equal to q of a. This is the same as saying that the additive inverse is unique, which we just proved. If you looked carefully at the proof we just did, we didn't really require there to be multiplicative inverses. What we really cared about was that two non-zero numbers cannot multiply to give 0. There are number systems where this is not true. For instance, mod 6 arithmetic. In mod 6 arithmetic, 2 times 3 is 0. All the other properties are satisfied except that property. So what if we used mod 6 arithmetic? Does this polynomial degree property stop holding? Yep, the polynomial x cubed plus 5x has 6 roots. It's 0 when x is 0, 1, 2, 3, 4, or 5. In mod 7 arithmetic, you can see that multiplying two non-zero numbers can never give you 0. So x cubed plus 5x, or any degree 3 polynomial in mod 7 arithmetic, would have at most 3 roots. It's so powerful and fascinating to be able to make such a statement, to figure out what structure of your number system makes a theorem become true. These structures are well studied and very useful, so obviously they have names. A number system with the properties we listed is called a field. Rational numbers, real numbers, complex numbers, mod 7 arithmetic are all fields. If you replace multiplicative inverses with just the requirement that non-zero numbers should multiply to give a non-zero answer, it's called an integral domain. Integers are the perfect example of a number system that is an integral domain, but that is not a field. If you don't even insist that non-zero numbers multiply to give a non-zero number, it's called a commutative ring. Mod 6 arithmetic is a commutative ring, but not an integral domain. I'll have to move on now, before we end up too deep inside all of this. I hope you enjoyed this edition of Blind Mathematics. Now we come back to our vision-filled world, to prove that the Chebyshev polynomial of degree d has a maximum slope of d squared. The proof I'm presenting will require a little bit of familiarity with slopes and how a maxima of a function is a root of its derivative. Let's take the degree 5 Chebyshev polynomial again. It has 4 places where its slope is 0. Since its derivative is a degree 4 polynomial, these are exactly the roots of its derivative. Now, since the derivative has these 4 distinct roots, at some point between each pair of roots, it must reach a maximum or minimum value. So the derivative of the derivative has a root between each pair of roots. That is, the second derivative of the degree 5 Chebyshev polynomial has 3 roots in this region. We proved in part 2 that the slope of the Chebyshev polynomial at x equals to 1 is d squared. We also proved in part 3 that the slope cannot be larger than d squared in any of the middle segments. So if the slope ever becomes larger than d squared, it has to be in one of the end segments, say this last segment on the right. But if the slope goes above d squared in that segment, it must be going from 0 to higher than d squared and then back down to d squared. That means that the slope has a maxima in this last segment, and so the second derivative must have a root in this last segment. But that would be a 4th root of this degree 3 polynomial, which is not possible. So the maximum slope is d squared. And with that, this series is finished. I hope you liked it. There might be bonus questions in the comments. Do check it out. Ask any lingering doubts, help out others, and of course, have a nice day.